All right, now we're ready to put together all those concepts that we've been discussing about the character of the salts to determine if they're acidic, basic, or neutral, right? We're going to put together our ideas from the cation and the anion to look at our salt overall and determine whether or not adding a salt to our water is going to give us an acidic, basic, or neutral solution, right? The first step is going to be to split our salt into ions. We're going to do that by drawing a vertical line down the middle and then saying that we have strontium 3+ and we have 2 Cl-, okay? Then we're going to identify each side. We're going to first start with our cation, our positive ion. We're going to walk our way through that. Some of you guys had a good suggestion to put our charge question first, right? So we're going to first look at whether or not the cation has a big charge, which is greater than or equal to 3+. Notice that our strontium has a greater than or 3+ charge. I'm sorry, in this case, strontium has a 2+. I guess I should be able to add, right? Because we have 2 chlorides that each have a negative, so that makes our strontium a 2+. So no, we do not have a big charge, which means that that implies pH neutral, right? Or rather, since we can't say that yet, because it could be a conjugate acid of a weak acid, right? So what we're going to first say is that it is not a small acid, right? We know that it's not going to be a small acid, and by small I mean that it's a small cation because it is just a single element metal, right? That was our metal cation part, okay? Step 2 is that the conjugate acid of a weak base, is that going to be our strontium? Is it capable of pulling OH out of solution? And the answer is no, right? Strontium is going to completely dissociate. Okay, so this is going to imply that since it was not a small acid and it was not a conjugate acid of a weak base, that this means that we are pH neutral for our cation. All right, now we're going to move on to our anion, which is our negatively charged species. Our first step is going to be to ask, is it a conjugate base of a weak acid? Is it going to pull H+ out of solution? Okay, well, we know that chloride is the conjugate base of a strong acid, and so it's not going to be able to pull H out. So that means that this is pH neutral for our cation, or sorry, for our anion, right? Now, in step 3, if you have a clear winner, right, then you're going to assign, right? These two match, so we know that our overall species is pH neutral, all right? So that would be the assignment of the salt overall. Now, if we didn't have a clear winner, right, like say that we had one that said it was an acid and one that said it was a base, then we're going to have to compare our Ks, and whichever one has the bigger K is going to win, and that would be what we assign, right? So to give you some examples, right, let's do aluminum bromide, right? So first I'm going to split it, so I'm going to draw my vertical line, and I'm going to write aluminum 3+ and bromide minus, okay? I'll move over my little B here, right? So for my cation, I need to ask, right, does it have a bigger charge, right? And the answer is yes, right? So we know that we have a charge greater than or equal to 3+. So that means that it is acidic, okay? So we don't have to do the other step, right? Once we know that it's acidic, okay, we don't have to do our second step. Then we're going to move on to our anion, all right? So we're going to look at the conjugate base, all right? So we're going to say our anion. Is it the conjugate base of a weak acid? Okay, and the answer is no, because if I were to add H+ to this, it would become HBr, which is a strong acid, which means that this is going to be pH neutral. All right? Acidic is going to be neutral. Basic is going to be neutral. Okay? So when we do the assignment, we know that it is going to be acidic. So we have an acidic salt. Okay? Now, since we've been able to assign it, we don't need to check our Ks. All right? Now, here we have ammonium fluoride. Okay? I'm going to split that, so I'm going to draw my vertical line, right, to split my 2 ions. I know that I have NH 4 plus, and I have my fluoride minus. Okay, my cation is the ammonium. Okay, my first question is, does it have a charge? Is it a metal ion that has a charge greater than or equal to 3 plus? And the answer is no. All right. Now, is it, when I add OH to this, does it want to keep the OH? And the answer is yes, right? It's the conjugate acid of a weak base. Okay, so that means that it is going to be acidic. All right, because if I added OH to that, it's going to form an equilibrium. Okay, then I'm going to move on to my anion, which is my F minus. So is the F minus the conjugate base of a weak acid? So if I add H plus to this, do I get a weak acid? And the answer is yes. Okay, so that means that it is basic. So I have a basic anion and I have an acidic cation. So that means I can't assign it right away. So I need to compare my Kas, compare my Ks. My Ka for the ammonium is going to be 5.68 times 10 to the negative 10th. All right, and my Kb for my fluoride ion is going to be 2.9 times 10 to the negative 11. Well, 10 to the negative 10 is bigger than 10 to the negative 11, okay? So that means that my Ka is bigger than my Kb, which means that it is going to be an acidic salt. All right? So that's how you're going to work through these salt problems to determine if they're going to make an acidic, basic, or neutral solution. All right? Now, the next thing that I want to talk about is how we figure out acid strength just by looking at different properties of the acids in their molecular form. All right, so to determine our acid strength, the first thing that you're going to want to look at is bond polarity. All right, when you're looking at bond polarity, all right, it must be polar along the bond to be acidic. The second thing is the dipole arrow, right? Since it's a polar bond, since there's some polarity, there's going to be a dipole moment. Okay, and if that dipole arrow points away from the H, okay, away from the proton, then that proton will be acidic. Okay, that means that it will be given up by the molecule. All right, now our third point is if as the bonds get stronger between that element and the hydrogen, as that bond gets stronger, that means that it's going to want to hold on to that proton harder. So if you have a stronger bond, you're going to have a weaker acid because it's not going to want to give up that proton as easily. Okay, so let's say that we are comparing HF and H lithium. Okay, so hydrogen fluoride and hydrogen lithiate, I think that's right. If we were to do that, right, then we would have, notice that in this case, right, the fluoride is more electronegative than the hydrogen. That makes the hydrogen a delta positive charge and the fluoride a delta negative charge. That means that we can draw our dipole arrow, putting the plus side near our delta positive, and we always point away toward the negative, okay? In this case, lithium, since it's on the far left of our periodic table, is actually going to be less electronegative relative to the hydrogen. So it's actually got a delta positive compared to the hydrogen, which means that we put our plus on the lithium atom and point away toward the hydrogen, okay? That means that for this one, since the arrow pointed away from the hydrogen, it was going to be acidic, and we know HF is an acid. In this case, with the HLI, right, our arrow points toward the hydrogen, which means that it's not going to be acidic, okay? Now, if we're comparing acids like HF, HCl, HBr, right, we know that HF has the largest dipole, then HCl, then HBr. Okay, and you can sort of think about it, right? We know that fluoride is smaller than chloride, which is smaller than bromide. Okay, so if you were to put a hydrogen, right, and make a bond, that means that this one can be held closer than this one, right? And that's at a larger distance. And then in the bromide, it's even farther still. Okay? So that means it's harder for bromine, because it's so much bigger, it's harder for it to hold on to that hydrogen, so it's going to give it up, right? So this has a stronger bond, because they're closer friends, right, than the chloride, which is going to be closer than the HBr. So this is stronger, slightly weaker than the chloride, okay? So that means that as we get stronger and stronger bonds, as we get stronger and stronger bonds, we get weaker acids. So if we get weaker bonds, right, so if they're not as good of friends, they're going to be able to give up their friendship. They're going to be able to give up that proton and donate it into solution and become a stronger acid, okay? So again, a weaker bond makes a stronger acid, all right? Now, the next thing that I want to talk about is sometimes you can look at it, at the structure, and say, okay, well, if I have an oxyacid, then I can compare those directly. So you're going to look for oxyacids. Don't worry, I'll explain what that means, right? An oxyacid is going to have the form where you have an acidic proton connected to an oxygen, connected to some other element, okay, that's electronegative, and it's going to be connected to a bunch of other stuff, okay? And you can see some examples of this on slide 45, okay? Or I would say 46 has the examples, all right? Now, here, notice that we have a proton connected to an oxygen, all right? I said Y was an electronegative atom, okay? And the more electronegative that Y is, the more acidic the proton is, okay? So think about it like this, right? Like say you've got a friend group, okay, and this is you, and you're really close to your friend Y, okay? If you spend a lot of time with friend Y, that means you're not going to spend as much time with the H, right? So if this is really strong, it's going to pull the electrons toward the Y. Well, if you pull the electrons toward the Y, that means that this one is going to drift off and become more acidic, okay? So the more that Y is electronegative, the more it wants those electrons, the more acidic that proton will be, because it can be given up more easily, okay? Also, if we add oxygen onto the electronegative Y, okay, it's going to make the acid even stronger, okay? You can think of it like saying, okay, let's say that, okay, let's look at all of these effects first, right? Let's say I have HOI, and I want to compare that to HOBr, and I want to compare that to HOCl, okay? Well, chloride is more electronegative than bromide, which is more electronegative than iodide, right? So we have increasing electronegativity. Okay, That means that my chloride wants the electrons more than the bromine, which wants the electrons more than the iodine. Okay? So if this is the strongest in pulling, like it's the most electronegative, that means that this is our stronger acids. And this is going to be weaker. Okay? So as we increase our electronegativity of the element that is attached to the oxygen, we get more acidic. Right? So that's that first idea. Okay? The second concept, all right, this is where I would almost recommend looking at the slide with the pictures of the oxyacids. Okay? In this case, let's say that we have HClO4. Okay? So I have, if I were to draw this, it would be HO, and then I have my Cl, I have one oxygen, I have two oxygens, and I have three oxygens. Okay? And then let's compare that with HClO3, which is going to be HO attached to Cl, and then I have two oxygens attached to my chloride, right? Well, I have three, but I have two additional ones. And then I have HClO2, which is HOClO. All right, and then I have HClO, which is HOCl. Okay, so as I add more oxygens to that electronegative element, right? So I had 0 that I've added. I've got 1, I've got 2, I've got 3. So as I add more oxygen, okay, so I've got more oxygen on my electronegative element, okay? That means that it will be more acidic, okay? Because all of these oxygens are taking time from the electrons and pulling them this way, which is making the the proton easier to get rid of, okay? You can think of it like if you've got a big group of friends, it's easy for someone on the outside of that friend group to kind of not get as much time, okay? And so they may end up leaving the friend group. How sad, right? But if you've got a small friend group, right, then that proton is going to want to spend more time with it, okay? All right, so that's basically the concept of our oxyacid structure, all right? And the last thing that I wanted to talk to you about is a different type of acids and bases, okay? So, up until this point, we've talked about Arrhenius acids and bases, and we've talked about Lewis acids and bases, okay? Now, we have Arrhenius acids. Okay, let's actually write this as a table. You guys can see the table on slide 47. Okay, and we have Arrhenius, we have Bronsted-Lowry, and now we're going to introduce a new type called Lewis acids and bases. All right, now your Arrhenius is going to be a proton donor. Arrhenius is also going to be, for a base, an OH donor. Okay, but remember this has to be in aqueous solutions. Okay, Bronsted-Lowry is a proton donor for an acid, and it's a proton acceptor for a base. Lewis is a little bit different. Okay, Lewis is an electron pair acceptor as an acid. Okay, so a Lewis acid is going to accept a pair of electrons, and a Lewis base is going to donate a pair of electrons. Okay, what do I mean by that? Well, basically, a Lewis acid is going to have an empty orbital that can accept 2 electrons. Okay, so if we look at slide 48, all right, then what you'll see is we have BF3, boron trifluoride. Okay, so we have that. Okay, and this is going to be a Lewis acid. Okay, because when I add it to a Lewis base, which is NH3, right? We have ammonia, and I'm just going to draw it on its side so that way I can kind of show you what I'm talking about. I always have one in the plane, one out of the plane, one back. Okay, so notice that I have this electron pair that I can donate to another molecule. Okay, when this comes in, right, the boron, right, it has room for 2 extra electrons. Okay, so this can donate into that empty orbital, right, and this happens to be a p orbital. Okay, it can donate 2 electrons into that p orbital. Okay, and then it ends up hybridizing to give you N, H, H, I'll erase this line, H, and H, and then it will form a bond with the boron, which is going to have a fluoride, has another fluoride coming out of the board, and another one going back. Okay, so in this case, this one donated an electron pair, so this would be a Lewis base, and this one accepted an electron pair, making it a Lewis acid. All right, let's do one more example on slide 49. All right, so let's say that we have aluminum 3+, and we add 6 waters. And I'm going to draw my water like this, where I have an O, H, and another H. All right, so I've got 6 waters. Notice that I have 2 sets of lone pairs that I can donate, right? Each of the waters is going to donate electrons into the aluminum. Okay, so we're going to end up with aluminum with 6 of the waters donated to it. Okay, and it all is going to have an overall charge of 3+. So if I were to draw that, right, you can think of it, I know that I have my aluminum, I've got 6 things attached, right? So I've got 1 up and 1 down. We always start that way, if you guys remember from lab. Okay, then I have O, H, H. It's donating 2 of its electrons up, right, to make the bond. And then we have another one up here. And then we have, since we're going to put the rest in the middle. We have 4 left, so 2 out front, 2 in the back. Got an H2O, 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 and an H2O. Okay, so notice that in that case, right, it's donating the electron pairs, so that would make this, since it's a donor of the electron pairs, that makes this a Lewis base. And since this accepts the electrons, okay, this is our Lewis acid. Okay? So whatever is going to accept the electron pairs is the acid, and whatever donates the electron pairs is the base. All right? And that concludes our discussion for this chapter. Good luck on your quiz. All right, those of you who are in my section. And I look forward to discussing our next chapter on even more topics for acids and bases.